Assalamualaikum warahmatullahi taala wabarakatuh. Today we'll continue about the relaxation oscillator, and this time we'll look into a square wave oscillator. Okay, square wave oscillator still use the charging and discharging characteristic of capacitor over here, and the capacitor and R1 over here at the at the negative feedback is a differentiator, and this value, the voltage across the capacitor of VC, is being compared with the voltage over here, which is the feedback coming from the positive feedback. Okay, so VC and VF will be compared, and the output over here will be determined by either VC is greater or VF is greater, and the output over there will be a square wave. Okay, so what you'll get here, your VC is being charged through this path. Okay, and this is during the positive output over here, but once the VC is greater than VF, okay, your output will be negative. VC is at the negative terminal, so when VC greater than VF over here, your output will go negative. When the output is negative, this is more negative as compared to this terminal, so C will be discharging its value through R1 right here. Okay, and once the VC is less than VF, since VF is at positive terminal, your output goes positive again. So this is what you'll get at the output, a square wave. This is the voltage across the capacitor. Okay, the positive output is also called plus Vmax or plus VO saturation, which is your VCC actually, and the negative Vmax or negative VO saturation is negative VCC. Okay, we're going to find the value of T1, the time taken for the C being charged. Okay, and also another time, which is T2, which is the output when it is low, and the time for C is being discharged. Okay, so if we look again, how does we get the output just now, square wave? When V out is positive, C is being charged through this path. Okay, your VC will be compared with VF. So we're going to find what is the voltage over here, which is the VF. Okay, so VC is being compared with VF. If VC is greater than VF, output will go negative. When the output is negative, okay, we have a negative output, and we'll have another value of VF, and C will be compared with this. So it is like a Smith trigger where you compare your input with two values, upper threshold and lower threshold. Okay, so now we look at when the output is positive. Okay, when the output is positive, which is this one, okay, your VF will be simply using the voltage divider, V out multiplied with R3 over R2 plus R3 over here. Okay, or I can write down is plus VO set R3 over R2 plus R3 over here, and this is the upper threshold point. Okay, so I simplified by saying that it is just beta VO set or beta Vmax or equals to beta VCC. Okay, so my beta is actually R3 over R3 plus R2, just to simplify this equation. Okay, and now when V out is negative Vmax, okay, when V out is negative Vmax, this is negative value. Okay, this is more positive, so C will be discharging through this path. Okay, and VF right here is your lower threshold point. It will be VO multiplied with R3 over R2 plus R3, and this is your lower threshold point. equals to minus beta VOZ, or minus beta max, or minus beta VCC. Remember, your beta is just the ratio of R3 over the whole R2 plus R3, just to simplify the equation. Okay, so now the output just now what we'll get is this. Okay, during high time, capacitor is being charged. During low time at the output, C is being discharged. So we have two time constant, T1 during the charging time or during the output is high, and T2 is during the negative output or low output, and C is being discharged. Your tau1 is actually this one. This is the path taken for the C being charged. So your tau1 will be simply R1 C multiply with C. Okay, and for tau2, the capacitor is being discharged during the negative output. So this is also the path. So your tau2 is also R1 multiply with C. Okay, so tau1, tau2 constant, timing constant, charging, and tau2 is time constant for discharging. Okay, so if we look closely at the capacitor being charged, this is the voltage across the capacitor. At time T1, we have, this is during the transition. Okay, when we comparing VC and VF, this is the transition, either VC greater or VC less than this node. Okay, so we call it beta max, the upper threshold point just now. Okay, but if we let the capacitor being charged over the time, meaning that when it reaches the steady state, the value must equal to Vmax, the maximum voltage of the output just now. Okay, the initial voltage is the lower threshold minus beta max just now. Okay, so this is the time for capacitor being charged up to T1. Okay, it will goes from minus beta max to positive beta max. Okay, why? So because this is when VC is greater than the VF. This is actually your VF. Okay, your output will go negative over here. Okay, so that's why it will be from minus beta max until the positive beta max. Now we are using the equation for the capacitor being charged, okay, and discharged, the same equation. Okay, so at VC at T1, the value right here will be plus beta max. VC infinity is when the capacitor is being charged over 5 time constant, it will reach the maximum value, Vmax. VC0 is the initial value, which is minus beta Vmax minus VC infinity is the value plus Vmax e to the minus t over tau. Tau is the time constant just now. For the charging will be R1C. Okay, so put it everything into the equation. Just now VC at time t, VC infinity Vmax, VC at 0 is beta minus beta Vmax, VC at infinity is plus Vmax e to the minus, we are going to find the T1 over tau1 R1C. Okay, so from this equation you have beta max, Vmax, so bring this over to this side and simplify this part, you'll get this. Okay, so beta max, this okay, I just rearrange the equation actually, plus beta max, okay, minus Vmax, you bring it over here, this is minus beta max, minus plus, because this is minus, it will be minus Vmax e to minus T1 over R1C. Okay, we are going to find the e to the minus T1 over R1C. So you have Vmax, 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 all cancel out, so you just left with beta minus 1 minus beta plus 1 e to the minus T1 over R1C, or it is simply 1 minus beta equals to 1 plus beta e to the minus t1 over r1c. I just change the value minus over here to positive, so it will be 1 minus beta over here instead of beta minus 1. Okay, so e to the minus t1 over r1c will be 1 minus beta over 1 plus beta, or this is minus negative value, so I can change it to positive, so it will be 1 plus beta over 1 minus beta, and then take natural log on both sides. Okay, this natural log of this, natural log of this, and it will produce t1 over r1c. This is from this, and it will be natural log 1 plus beta over 1 minus beta. So my time t1 will be simply r1c, which is tau 1, natural log 1 over beta, 1 plus beta over 1 minus beta. Okay, so that is for the charging time. So now we look at the discharging time. It will look like this. Okay, so this is your initial value plus beta max. Okay, when it is discharging, if you let it to be discharging over the time, you will reach the minus Vmax. Okay, but it won't reach that value because we are comparing with the minus beta Vmax, which is your Vf just now. When your Vc is less than minus beta Vmax, your output will go positive again. So that's why it will reach up until here, and after that will continue your output. Okay, but this is your Vc. So using the similar technique in finding T1, we'll get this. Okay, and if you notice this equation, T2 equals to R1C, natural log of 1 plus beta, this is the similar equation with T1. Why? This is because the capacitor just now is being charged and discharged through the same resistor R1. Okay, so for the time taken or for one cycle or one period, it will be T1 plus T2. Just add up those two, so it will be 2 R1C, natural log of 1 plus beta over 1 minus beta. That is your time for one cycle. Okay, remember beta just now is R3 over R3 plus R2, so just plug in this beta into this equation, so you'll get 2R1C natural log of R2 plus 2R3 over R2, and frequency is 1 over T, it will be simply 1 over 2RC natural log of 1 plus beta over 1 minus beta. So this is the frequency of oscillation for your output, which is a square wave. Okay, so next is triangular wave. For the triangular wave, it used the operation of integrator. Okay, so this is your C, R, and it is connected to a switch over here. This switch is connected to minus Vc and plus Vc. So what will be at the output? Okay, so first we look when the switch is at position 1 over here. Okay, meaning that you are connecting R to a negative value. What you'll get at this output, this is negative at the input, and this is inverting terminal. So your output will a positive going ramp. Positive going ramp. This is how it looks. Your switch at negative V, which is position 1. This is your output, a positive going ramp. Okay. Now, when the switch is at position 2, this switch at position 2, it is connected to a positive supply. Positive going into the negative. Okay. So your output will be a this is positive input going to the negative terminal, so your output will be negative going ramp. Positive input, output will be negative. This is how it looks. Okay, this is switch at position 2, input is positive, output will be a negative going ramp. Okay, so now if you put the switch to position 1, position 2 repeatedly at a regular interval, okay, so what you'll get is the alternating positive going and negative going ramp. Okay, so this is how it looks, the output. position 1 positive ramp,